Awesome. Thank you so much for the introduction, yeah, for having me. So today I'll be talking about using computational fabrication and assembly to enable manufacturing at points of need. And the word robot isn't in the title, so not to dissuade you from listening. But most of the work I'll be talking about today has either appeared in robotics venues or are generally about trying to design and fabricate robots or using principles from modular and reconfigurable robots to perform assembly. But the key kind of challenge we're interested in is trying to enable end users to design and fabricate stuff at points of need. And so to kind of illustrate why I think this is important, I'll start with a particularly kind of noticeable point of need, which is the space environment. So anything we launch to space today has to fit within the confines of a rocket fairing, which is typically no larger than 3 or 4 meters in diameter. And once we package our robots or our structures into these rocket fairings, they then have to withstand the rigors of a launch, which can be upwards of 9 Gs. And once these artifacts reach orbit, they then have to be either assembled or maybe maintained or even repaired by teams of people who don't necessarily have manufacturing experience in some of the harshest conditions that we know of. But these challenges are mirrored on Earth as well. So in hospitals, in laboratories, in disaster areas, and even community makerspaces, these are all kind of environments that require unique hardware solutions with both speed and customization that a kind of centralized mass manufacturing paradigm that we have today doesn't really provide. And this is because centralized mass manufacturing places some pretty hard constraints on our ability to customize individual items for individual needs and interests, to deliver them to the right places at times of need, and also to transport them across not just global, but increasingly extraplanetary supply chains, which are subject not just to kind of volume constraints as they're shipped, but also to global political and economic stability. And so I think creating new manufacturing capabilities that can be deployed at these kinds of points of need requires addressing 2 key challenges. So on the one hand is portable hardware systems for fabrication that can operate autonomously outside of these traditional manufacturing ecosystems. And second, we need new software tools or new design tools to actually allow users to design new things that these hardware platforms can actually produce. And so in our research, we generally co-develop hardware and software systems to allow end users to design and fabricate things at the locations where they are intended to be used. So to kind of illustrate how we think about breaking down problems to be solved, I want to start with a kind of toy problem. So I played kind of the first things I built stuff with was with Legos. Probably the same thing applies to many of you. But Legos provide some kind of unique capabilities. So they can be transported compactly. They can be assembled in very complex geometries. And they can also, maybe most importantly, allow this to be done easily. So I wanted to kind of highlight 3 attributes that I think make Legos such a powerful platform for manually assembling stuff, and talk to you about why or how we can use these to automate assembly. So first thing is that they can generally be assembled by a single person, or a single robot arm. Second is that they're modular, right? So their kind of base unit is a rectangular prism that can be stacked and tessellated in lots of different arrays to make these complex shapes. Third is that they're attachable. So they're patterned with these kind of selectively paired studs on top, which allow them to snap to each other in aligned configurations. So so in this talk, I'm going to talk about 3 different research themes that kind of show how we can exploit each of these features to enable and automate assembly at points of need at 3 different levels: at a machine level, at a part level, and then at a material level. So the first of these levels is this idea of hybrid manufacturing machines, where the kind of long-term vision is that if we can replace a person with a single integrated fabrication platform, we might in the future be able to package the capabilities of today's factories into the size of tomorrow's 3D printers, and really allow to fabricate individualized, customized artifacts at points of need. The second is modular assembly platforms, where the idea is by augmenting the static parts with embedded actuation, can we produce modular parts that can be transported compactly, shipped to a location, and then autonomously reconfigure into target shapes, which would allow us to kind of reuse our existing infrastructure instead of always fabricating them from the ground up. And the last of these themes is this idea of programmable materials, where, coming back to the Lego example, if we can replace these geometric studs we saw in the Legos with selectively programmed materials, we might be able to really simplify and accelerate assembly by creating materials that will want to align and assemble themselves. So in this talk, I'll highlight kind of examples from each of these themes. I'll start with showing how we can start to build mesoscale artifacts like robots in a single platform. I'll then talk about an inexpensive desktop machine, which we can use to create custom metal parts in 3D. And then I'll kind of switch gears and talk, the first two projects are kind of about machines. And I'll switch gears and talk about more modular robotics, reconfigurable robotics themed projects. Where in this one, I'll talk a little bit about how we can start to think about modularly self-assembling space structures that are larger than what any traditional fabrication platform can produce on its own. And finally, I'll talk about how we can program magnetic materials to create these highly selective and self-aligning features that can accelerate assembly. Okay, so I want to start by talking about one of these projects that highlights one of these hybrid machines. So in collaboration with Microsoft Research, we worked on this project where the goal was to create custom electromechanical artifacts like robots in a single platform. So our goal was really threefold. We wanted to make one standalone machine that can do three things: to create the geometry of a part, to print its circuit traces, and then to assemble some discrete components. And so the way we kind of tackled this problem was, so the way we make these functional devices is by using a custom-built hardware add-on that clips into a laser cutter. And this hardware add-on can augment the native laser cutting capabilities with a silver paste extruder which can print circuit traces, and uses a pick-and-place mechanism to assemble components. And we use the laser itself to not only create the geometry of a part, but also to later sinter or cure these silver circuit traces, which we'll see in a second. So I'm going to play this 1-minute video, which goes through the full end-to-end fabrication process. So this process starts with using the laser to cut out the perimeter of an object, which in this case is a quad rotor. Next, we use an onboard silver paste dispenser to deposit these silver circuit traces. These traces are a silver nanoparticle embedded in a resin matrix, and it's non-conductive in its liquid state. We'll see in a second how we make it conductive. And next, we use this onboard pick-and-place mechanism to collect components from a storage area that's over on the right, and we deposit these components onto the substrate, where we're lining up the pins or the electrodes of each component with the circuit traces we just deposited. And then finally, we use the same laser, this time in a defocus setting, to actually heat up and sinter or cure these circuit traces. And this has the dual effect, first, of electrically connecting all of the components, but also of rigidly bonding them to the board. So in the case of a quad rotor, it's now fully connected and can deploy itself directly onto the platform. So I wanted to show this kind of brief simulation of what the hardware add-on. It's built from just $150 worth of commercial off-the-shelf components. So this is what it looks like. So it mounts directly to the head of a laser, and it consists of a housing which attaches to this laser using some 3D printed clips. It houses a couple of serially connected batteries which power a microcontroller and some electronics. And this controls a pump, which acts through a series of solenoid valves to control our silver paste extruder. And then separately, we have our pick and place mechanism, which is driven by a stepper motor, which acts through two serially connected linear potentiometers to our pick and place syringe. And together, this provides a compliant transmission, which we can use to pick up objects of variable heights.
Mark, how does that pick and place grasp the individual objects?
Yeah, so it's just like a kind of a commercial off-the-shelf little syringe with a little kind of suction cup on the bottom. Yeah. So I just kind of zoomed through the fabrication process and what the hardware looks like. So next I'll just kind of switch gears and talk about the software pipeline or the design tool we use to actually design these artifacts and how we transmit them to the machine for fabrication. So we built a custom interface as a plugin to Adobe Illustrator, where you can just drag and drop parts from a part library onto this canvas, and then use a set of circuit tracing tools to connect these components with these little green wires, which stand in for the circuit traces. And then we can go to our geometry tools and start to place cut lines. So these red lines are going to be what's defining the perimeter of the quadrilateral. And once we've finished the design, our system can then animate the full sequence of fabrication events that we can check for correctness. So going through, again, all these steps from cutting to silver paste deposition to part placement, and then finally sintering. Yeah.
Does it generate the cam autonomously?
Yes, and that is my next slide.
Nice.
Yeah. Yeah, so yeah, that's a great question. So once we've designed these files, we then run a post-processing script that translates this user-defined file, this design file, into a manufacturing file that we deploy directly on a machine. So this is what a kind of simplified version of what the manufacturing file looks like. So a couple of things are required to get this to work. One thing you'll notice is that we have these cut lines shown in red and these soldering or sintering lines shown in purple. And they're directly superimposed because these are all kind of the sintering is taking place inside of the cutting geometry. But you'll notice that the trajectories for the silver paste deposition in yellow is totally offset from the cutting lines. And this is required to offset these two to reflect the physical distance between the laser and the silver paste dispenser physically on the machine. We have to do a few other things. So we also have to automatically generate these pick and place trajectories so that our tool head can collect components from the storage area, which is defined by abstractly by this dashed line, and then place them on the substrate. And we have to do this in a way that guarantees collision-free placement of the parts. And then we also have to make sure that no matter what order a user designed this design in, that we can correctly execute sequentially the manufacturing processes the way they're supposed to be done. So like, sintering has to take place after circuit deposition. So one thing I didn't talk about was how our hardware add-on actually communicates with our laser cutter, or how it actually communicates with the laser cutter firmware. And it's because it doesn't have to. So we came up with a trick where during the post-processing stage, we automatically append these extra lines at the start and the end of every circuit trace. So you can imagine that this line here is the beginning of the circuit trace extending to the right. And we automatically append two lines above this on top of it in the SVG file. What happens here is that when our laser cutter sees this in the manufacturing file, it's going to try to execute these two lines before it executes the silver path. And we use an onboard accelerometer to detect this jiggle. And we use a classifier to make sure that we know that for a given kind of signal, a given kind of oscillation, we know what fabrication process to initiate. So this GIF kind of demonstrates this feature to start silver extrusion. where I've magnified this little jiggle at the beginning. And so what's nice about this method is that because there's no direct communication between the hardware add-on and your fabrication platform, we can effectively deploy this hardware add-on on any manufacturing system, or certainly any laser cutter. Yeah.
But still,
Oh, sorry?
the cool confused with the back and forth.
Yeah.
Is this part of a calibration process or?
Yeah, so whenever we have, for example, a circuit trace, we'll append these little lines that result in this jiggling action at the start and at the end of that circuit trace. And so in the fabrication instructions that are given to the laser cutter, the first thing it does before it tries to extrude silver paste, before it goes along the path that the silver should be deposited over, it first executes this little jiggle. And we have an onboard accelerometer that can detect this jiggle. And we have a motion classifier where we've characterized that to be associated with like start silver extrusion or stop silver extrusion. Does that make sense?
So you're basically using these as perimeters,
Uh,
like as separators for between different operations.
yes, yeah. I mean, essentially, yeah. For now, we use it to trigger, so to start silver extrusion, to stop silver extrusion, and the same thing with pick and place. So to descend, to pick up, and then to descend to place. So yeah.
Just to make sure, like, to recap, so I actually understand, because I actually think it's illegal. So you did not want to talk directly to the laser cutter software itself. So what you had to do is you had to offset the initial drawing for the tool offset. So like the laser is actually offset because the paste is like 150 millimeters behind. So now your tool head, that's the laser cutter, is in its weird position that you already offset. But you still have no way to say deposit the paste as I'm going. So you said, okay, let me wiggle the laser cutter. And then when you wiggle the laser cutter, the controller says, oh, we have to do paste, start depositing while we trace, and wiggles to say, okay, hey, we're no longer moving the laser head. We no longer have to paste.
Exactly.
That's really cool.
So because some laser cutters might be easier to talk to than others.
Yeah.
We were using maybe I should have name dropped it. We were using one which wasn't very kind of open source friendly, and so it proved to be very difficult. So what we actually did was later on, these laser cutting files was written as SVG files, but we converted this kind of little this jiggle into G code, and we showed that we could just take our add-on and just stick it onto a 3D printer head, and it works exactly the same way.
Does that mean you end up with a little extra blob of solder paste at the end?
Yeah.
Before it realizes that the end jiggle is telling it to stop?
So if the jiggle can happen fast enough, it doesn't. It doesn't happen.
Oh, you said this one's like exaggerated.
This one exaggerated.
Okay.
Exactly. Yeah. That's exactly kind of one of those many characterizations we have to do to get it to work well. It also helps with you can do things like cool down your silver paste so it's much more viscous before deposition, which also helps. But there's lots of different things we can do to make it better. Okay, so because we don't have this, we don't have to do anything in terms of communication between the hardware add-on and the cutter. It means setting up for fabrication is super straightforward. So all we have to do is mount this add-on to the laser head with a couple of 3D printed clips, insert our material, and then we're good to go. And so put together this, oh yeah, sorry.
Martin, do you think this could work with 3D printing as well, since it's extrusion?
Yeah, like mounting this kind of
Like you can laser cut and print at the same time, 3D print.
Yeah, I mean, yeah, I can imagine a system where we basically added an FDM print head onto a laser cutting platform. I think
It's super exciting.
yeah, I don't think I've seen that before, but it's an interesting idea. Yeah, exactly. Yeah. So put together this kind of end-to-end system affords a range of other functionalities as well. So one thing we can do is create more complex PCBs using just a standard library of parts. So here we're creating an H-bridge using a set of transistors and resistors. We can also quickly cut and stack material to create 3D geometries without the support needed for overhangs, which you might typically find in a normal FDM printer. And we didn't publish it in this paper, but one thing you can also do is focus the laser at the interfaces of these materials to actually bond them together. So they won't just be sliding on top of each other. We can also create 2.5D electronic devices in another way. So here's a kind of simple lamp that's fabricated in one go. And the kind of intended use case is that it kind of clips onto the top of your laptop to provide lighting for the desk over to the right. And so we can fabricate this in one go by using the laser to heat up our material until it becomes compliant and then folds under its own gravity. And we can write our circuit traces in a way that straddles these hinges. So you'll see the light turn on here at the end because the circuit's electrically connected. We have this fully functional device before we even remove it from the laser cutter. So I just introduced this example of a hybrid machine where we showed by kind of consolidating different manufacturing processes in a single platform, we can build these small mesoscale artifacts like simple robots in one machine. And the common kind of digital fabrication machines, or the most common ones in use today, which are primarily laser cutters like the one we showed here, as well as FDM 3D printers. Both of these provide a really good foundation for kind of hybridization in this way. But in particular, the most common kind of printer that is in use today is these FDM printers. And two of the reasons why they're so great is that they're super inexpensive. So you can buy a pretty good one for around $300. And they're also very compact. Generally they're about the size of a microwave, so you can kind of put it on your desktop. But one of the problems with these kind of really accessible, inexpensive machines is that they can typically only print stuff out of plastic. And so the stuff we print with generally isn't very strong, not very stiff, it's not very recyclable. We generate a tremendous amount of waste, particularly in the rapid prototyping phase. So in this next project I want to talk about, a project where the goal was to see if we can create a digital fabrication machine that's really, really cheap, that's really, really compact, but can produce parts out of metal, particularly aluminum. So in this project, we made this kind of end-to-end design and fabrication pipeline where we have a machine that can take a rod of metal and then bend that metal into 3D shapes. We originally thought about trying to use additive manufacturing, but it turns out that trying to do additive manufacture with metals requires some pretty complicated machinery and wasn't really going to let us build a machine for $300. So we bend parts out of metal. And we do this using 3 different operations. So we are feeding in an aluminum rod from the left. That's one operation. Our end effector will bend that metal to a 3D shape. We also have a rotate operation, which rotates the bending plane. I say without the rotation aspect, we basically built the glorified paperclip machine. It tends that actually is how you make paperclips using these bending operations. So these fabricated geometries, they take about 60 cents in aluminum material cost to print. We can bend objects like the one you just saw in around 3 to 4 minutes. So it's drastically more, drastically quicker than FDM printing as well. And the machine itself is built from around $295 worth in commercial off-the-shelf components. And we designed it from scratch specifically such that it can be assembled primarily from 3D printed components. So you don't have to machine too much to get this thing built. So the machine itself can be broken down into a few key sub-assemblies. So first off is the feed assembly. And this consists of a pair of stepper motors that essentially grip our feedstock and translate it, pull it through into our bending sub-assembly. And we have this sub-assembly, which we affectionately call a tail rail, which is basically where we clamp the distal end of the rod into just to constrain it in rotation while we're feeding it forward and to support the distal end. The bending assembly over to the right is the sub-assembly that actually performs the bending operation. It's the only part of the system that actually deforms the material. And this rotation assembly is there simply to rotate the plane of the bending. So that turns the entire bending assembly. And finally, the frame houses our electronics and holds everything together. So the question that you had was, how do we go from a wireframe design into a fabricated artifact? And maybe more importantly is, how should we try to get users to design this thing in the first place? Because it's not super intuitive how one would wish to design something like this. And so we created a pipeline where in the design phase, you can start by uploading a 3D model, and then we convert that into a wireframe. And once we finalize the design, we can run again a set of post-processing instructions that will turn that design file into a set of fabrication instructions. We also bake in some error correction that try to adjust for error sources in our materials, as well as the geometry of our machine, which I can touch on later. And then finally, we basically generate this, our version of G code, this text file, which we can upload to our machine and then execute fabrication. So I'll just kind of talk through these first 4 steps above. So in our design tool, which I'll show a couple of videos in a second, we start by prompting a user to upload a 3D mesh, a 3D model, like this cube. And then we ask the user to trace out a wireframe across this cube. So you can click on the vertices or corners of this mesh, and it will automatically append those lines with edges to construct an initial wireframe geometry. We then represent that wireframe as a graph, and we do some simple path planning through that graph, where we're searching specifically for an Eulerian circuit, which means that we're looking for a path that covers every edge exactly one time. And if that constraint is satisfied, this means that we can bend the 3D geometry from one continuous length of wire. And once we're happy with that design, we can export that 3D path, and then perform all this processing to turn it into fabrication instructions for our machine. So I'll just kind of play through a couple of videos that show how we actually use this design tool to make exactly this cube. So we have this interface that's written in Python in the Blender environment, where we can start by uploading a 3D stencil, like this cube. Now we're going to click through the vertices of this cube. We're just going to leave behind this wireframe. Might be a little bit hard to see. It's these black lines. After we have that initial wireframe, we can move around vertices and edges. We can add vertices, delete edges. We can augment this as much as we want. And once we're done, we can run a series of fabrication checks. So I won't talk in detail about what these visualizations mean, but we can check for path continuity. We can check for whether we're satisfying or violating any maximum bend angles that a machine can execute. We can also check if we're violating any minimum edge lengths, which is also a machine-specific constraint. Once we're satisfied with our design, we can then animate the fabrication instructions. So here we're animating the sequence of fabrication instructions we'd expect to see. And we can use this to check just manually for now for collisions. And at the end of this process, we can export this as our kind of custom G code, which consists of a sequence of feed, bend, and rotate commands with an argument. So this is kind of like a custom slicer, where we kind of visualize things layer by layer and then export this G code. So then we take this text file, we upload it to our machine, and then we can just execute these commands. And we do some extra steps here. I mentioned error correction. We also have to do things like add some homing instructions and other stuff to make this work. So right now, we actually just finished this project pretty recently. We're presenting it next week. This kind of first milestone was to see if we can build this end-to-end pipeline to try to kind of recreate with these aluminum wireframes some simple objects that you might typically 3D print today. So we kind of, so this was sent to an HCL, no, yeah, to well, it doesn't matter, but we focused on some kind of human-computer interaction applications, trying to recreate household objects. I don't know how much struggle you have with your cups when you go to Starbucks. So here we have a cup holder. Here we're printing a pegboard. I think a lot of the students working in the lab right now like to play a lot of Xbox. So this is one of their ideas. And I'll just let this video play. I think there's this geometry and then one more. So right now we're able to make these centimeter scale items. But one of the kind of research directions I'm really excited about is whether we can build a machine like this that can produce kind of a large kind of meter scale structures, particularly in a microgravity environment. Because you can have a platform now where you have this small kind of desktop sized machine, which you can launch together with a big spool of material and launch that to orbit, and then it kind of extrude, meters and meters of this material to create larger scale structures. That's kind of like the vision for this project in the next few years. Yeah.
Do we have any kind of compact notion of what is the space of designs that can be realized by this?
Yeah, this is kind of like the big problem we have to solve to kind of make this really useful. So there is some existing work. So two of the main problems, there are a few problems to solve. So one is that not every graph has an Eulerian circuit. So like a simple example of this is like a T. You can go up the kind of route, then you have to turn left or right, so you can't do both. So there are techniques to get around this. So you can, for example, add double edges to some areas of the graph. So you can kind of turn one way and then go back. There are also physical constraints. So our bending machine can't bend all the way to 180 degrees. That's not because of the machine design, that's because of the material itself. So aluminum is elastic. It exhibits a phenomenon known as spring back. So if I bend it to 90 degrees, it's going to spring back to 80 degrees. If I bend it to 180, it's going to go back to roughly 170. So those are kind of some of the big problems. I think another kind of, another challenge is how much of this we should try to automate. So like we had an idea in the beginning of whether we should take a mesh and just kind of automatically find a path that was fabricable and then give that to the user. We have this interesting kind of conflict here where the user might have a very specific idea of what they want. And if you kind of perturb that mesh or adjust some of the edges or add an edge here or remove an edge there, the wireframe design might not be what the user intended to in the first place. So it's a really tough problem, but I think it's one of the big ones to solve. Yeah. Yeah. Oh, sorry.
Do you, in the long run, do you intend this solely for static structures, or have you considered adding some sort of like joint module that you could insert along the way? I'm just thinking like, if you did, then it becomes sort of almost exactly the same design space as the tubular stuff I showed earlier.
Exactly, yeah. So one of the things we're working on right now is to automatically generate joints for these structures, not just so that we can rigidize them, because right now they're kind of open circuits, so they're very compliant, but also to allow us to build many of these structures so we can then join together. And we're looking at joints that are not just static, but can also articulate. So can we rapidly prototype these large designs that can actually have some dynamics to them? Yes.
You talked about scaling this up to meter scale so that in microgravity so that we can find big structures, but like is there a like will it be viable to do it for the smaller thing as well, like millimeter scale, for example? Like because I can see that it will require some kind of gap just for the mechanism to fit there.
Yeah, so is the question basically, can we go smaller instead of bigger? Yeah, it's a good point. We haven't thought about it too much, but I suspect that you could. I don't see any immediate reason why it would be challenging. So when you go larger, particularly in a gravity environment, you have to take into account, sagging. But if you go smaller, I imagine things might get easier. It's a good idea. I have to think about it. Do you have any ideas?
Another point that I was thinking about is you mentioned bend back, right? Like you bend it to 90 and then it touched to 80. Will heating up the material, even the rod a bit, before bending it, solve that?
Yes, I think it would. Yeah. I think there's a few things we can do. We can try to heat it up. We can use more compliant materials. We might be able to move to tubular wires instead of solid wires. So I think there's a bunch of stuff we could do to try to make this better.
Also, I'm sorry, I'm asking.
No, it's okay.
There are these memory shape alloys as well, right? That you can. So can one pre-print these, then send it somewhere, and then just heat it up to get it back into shape, because it is considerably simpler to ship flat things than 3D structures.
Exactly. I'm so glad you asked. So that is something we've been thinking about, and we've already bought some SMA and we're playing around with this idea. Yeah, right, exactly. So like I said, there are two ways you could use that, but I think the most compelling way is what you described, which is, can we bend the SMA into some target shape and then bake it, program it into that shape?
Right.
So let's say we bend a cubictahedron, we program that shape, now we can squish it into a ball onto a sheet and then send it somewhere. They can heat it up and
even some origami can come into it.
Yeah, I think that's a great idea. Okay. Yeah, thanks for those questions. Okay, so to summarize what we just saw, we just talked about two different fabrication machines. We introduced different manufacturing processes to try to kind of exploit different phenomena to make parts using a single machine. But there are kind of many instances where we don't want to rely on an external machine for self-assembly. For assembly. Where we instead want to try to use self-assembly to reconfigure what we already have into new shapes. So this is the kind of the point of the talk where I'm switching into modular stuff. So as we've already kind of hinted at, one such application is space structures, particularly optical telescopes. So we want to kind of leverage the most advanced of our manufacturing processes to make optical telescopes here on Earth. But the size of all spaceborne telescopes is limited as a result. So one way to get around this is, of course, to chop those telescopes up into parts, store and launch them in parts, and enable them to self-reconfigure when they reach their targets. And so working at the European Space Agency quite a few years ago now, but continuing at MIT, we worked on a framework to allow structures to be partitioned into modules or voxels before self-assembling into target shapes on orbit. And we allow this reconfiguration using electromagnets. So we built these modules that are around 50 millimeters side length, and we embed these electromagnets in their edges, which allow them to pivot with respect to their neighbors. And so the electromagnets are these kind of golden or copper-colored things that look like cylinders in the edges. So to show how we kind of use pairs of electromagnets to enable this pivoting technique, I have this slide where we have two of these voxels, and I've color-coded 4 electromagnets according to the direction in which they're polarized. So you can imagine red electromagnet, north pole facing you, blue electromagnet, north pole facing into the page. And so if we have 2 electromagnets that are polarized in different directions, they're going to attract each other, they'll form a hinge. And 2 electromagnets that are oriented in the same direction are going to repel each other, which we can use to actuate the pivot. And so after we've kind of launched and are into the travel phase, we can maintain the hinge with the electromagnets, with the attractive electromagnets. And once we complete the pivoting maneuver, we can energize a second pair of electromagnets to kind of lock or stabilize the 2 cubes after they've completed the maneuver. And we chose cubic modules for a reason. So it turns out there are lots of useful algorithms out there that show that we can, if you have some 3D structure that's been discretized into voxels, there are ways you can reconfigure that structure into a new structure. You need to update this so it says UW. I've taken this image from a paper from Cynthia Sung a few years ago, who of course has done some awesome work in this space. But the point I want to make here is that many of these algorithms require you to be able to perform two key primitive maneuvers. So one of those maneuvers is a simple pivot, where we have two cubes that are pivoting around a shared axis. And the second maneuver is a traversal, where one cube pivots off the face of a second cube and onto the face of a third. And so our key goal with this particular paper was to show that we can use our electromagnetically actuated pivoting technique to perform these two maneuvers, so that we could conceptualize how we'd reconfigure larger arrays of these structures in microgravity later on. So we built an array of modules, and we started with testing them on an Airtable in the lab. So an Airtable, if you've ever been to an arcade, it's like an air hockey table, provides these little cushions of air, and you can use that to simulate microgravity. So in this video, we're going to use these electromagnets to perform the simple pivot maneuver. And all these videos are in real time, and they're being commanded from a laptop out of frame. So that's the pivot maneuver. And next, we do the same thing for the traversal. Turns out it's very difficult to hold 3 cubes with one hand, so it takes a little time to set up. Once we turn on our machine, we can then execute these traversals as well.
You ever find that we get stuck partway between two configurations where like both edges were able to attract each other?
Like during the traversal, if it got stuck in the middle?
Right, like if it bumped into something and now there's only one edge, but it's no longer moving towards its next attracting edge.
Yeah, I think I expected to see that problem, but then we didn't. It turned out it was actually very easy to get it to work on an Airtable at least. I guess the reason being, as long as you have a big enough push, there's very little kind of viscous forces or friction on this Airtable to slow you down. So as long as you start moving, you're almost guaranteed to meet to collide with that cube you're pivoting onto. And the same is much more true in microgravity as well.
Do you expect to encounter any issues with noise when you scale this up? Do you think having electromagnetic is very close to a bunch of devices being wireless?
Oh, interesting. If we scale up?
If you scale up to many cubes or more cubes, and you have relatively strong electromagnets next to a lot of different devices all communicating wirelessly, do you expect to run into any noise issues around like the ability to scale it up, or just?
Yeah, it's a great question. I don't know. I don't know exactly. It's definitely something we would want to check for. When I've thought about scaling up, I always wanted to do. I never imagined we'd make a wireless system. I guess for the systems I was envisioning, I figured that we'd have to do power transfer between the modules. And so I always imagined us having a solid connection between all our modules that they could also communicate through. So maybe I haven't thought about that problem enough, just because we expected to do some kind of solid connection for communication. But yeah, I definitely would expect something. Yes.
So this is a continual question with what David just asked. It's about you taking advantage of inertia to launch and then assemble. So what if you have some sort of cube that is it starts in the in-between configuration or something? Is the electrical magnet strong enough to sort of hold it there, or do you need some sort of clever way to push it?
I think it would be very hard if it got kind of lost along the way. It would be very difficult. For these electromagnets, the kind of force to distance function has terms to the second and fourth power. Essentially, the force decays very rapidly with distance. So we want to send a really high current to the electromagnets right at the start, and really blast it so that we can kind of generate enough force while they're close together to send on its way. I think because the interacted we can only generate forces over such small distances. This is also why we didn't think too much about the problems of wireless communication as well. Yeah, does that answer your question?
Yes, and
Yeah.
does that mean that in this case, it benefits if you try to make this cube smaller? Because then the cubic force law, square law will be better.
Exactly. So the cube, this design that we have is kind of designed for microgravity. It's not at all strong enough to pivot against gravity modes. And exactly as you suggest, to try to pivot in a terrestrial environment, you would really want to scale down quite drastically. We started working on a prototype actually. We tried to miniaturize this to around 10 millimeter edge length. Then you have a different problem. Then your problem is electronics and trying to miniaturize electronics, and then substituting like better core materials. So like here I used ferrite. So like, one of these electromagnetic cores cost maybe 5 cents. We brought in some permalloy, which is a different material, has a very high flux density, and a core like this cost around $90. But it can carry about it can provide about, for the same volume, it can give around 16 times as much, generate 16 times as much force.
60 or 16?
1.6. So there are lots of things you can do to try to do better, but you have to go smaller. You have to pay more money, I think. Yes.
The only benefit of trying to use triangular structures, right? And or maybe also putting ratchets on the edges.
Yeah, I like the idea of ratchets. But to your first question, yeah, we thought a little bit about different space filling polyhedra that we can use for this software configuration. So you can imagine maybe it probably would work for tetrahedra as well as some other geometries. One reason we settled for these cubic shapes is first that we can do things in Cartesian coordinates. It makes it easy to kind of localize things. But also, even though our intention was to go to microgravity, if you don't have cubes, it makes it difficult to test on a 2D surface. Because all the planes line up. And so we can test these pivoting techniques on an Airtable in the lab before we even deploy it to microgravity.
I mean, so like if you bisected the cube diagonally, you could easily reform cubes. Presumably. And you could also form other things, Eiffel Tower. And that's
Oh yeah, but so you mean like if you were to have like these like triangular shapes?
Yeah.
Then yeah, so I think conceptually that I think it would be very interesting. It might just be more difficult to test all aspects of the reconfiguration. Experimentally, I mean. Yeah.
Also, for the sake of time, we should allow Mark to finish his talk.
Okay, I'll try to go faster. Okay, so we showed these two pivoting maneuvers work on an Airtable. And then ultimately we took our cubes on a parabolic flight to demonstrate that we can use this technique to reconfigure things in microgravity without the kinematic constraints of the ground plane. So here we're entering a parabola. I'm going to hold these cubes in the center of the compartment, and I'm going to wait for stable microgravity to settle. You can see the people start floating behind me. And once microgravity settles, I can release the cubes and we can execute this. I was very happy. You can see that's fine. So wait. This is just showing the same video, but from a different angle.
That's great.
So I know we are running out of time a little bit, so I'm just gonna add an overview slide here, kind of delving into some of the details about how we made all this stuff work. I see we're approaching 5, so I'll skip through some of this. And I'll just end this project description with kind of giving an overview of the hardware. That was kind of the centerpiece of what I wanted to talk about anyway. But a lot of the work that we did went into how to design the electromagnets and the electronics used to drive them. And so we ended up designing and fabricating these electromagnets. And then to build our electronics, we ended up spinning out these PCBs that consist of a microcontroller, a wireless module, two 16-channel GPIO expanders, and then 6 dual H bridges. And all this means is that we designed our PCBs just so they can drive 12 electromagnets bidirectionally. That's their only purpose. We then have these PCBs mounted inside this 3D printed scaffold. And the batteries, which are over here, which are the heaviest part of our structure, they're kind of sandwiched between our two PCBs right in the middle so that we minimize rotational inertia. And then finally, I have this really brief video just showing a little work we did to come up with a design tool in order to be able to plan some of these reconfiguration maneuvers and calculate which electromagnets have to be polarized and when. So this design tool lets us do a couple of different things. We can display our cube IDs and our electromagnet IDs. We can directly manipulate individual voxels. We can also visualize the particular electromagnet assignments. So here shown in blue and red. We can also visualize which voxels have to be unoccupied in order to perform a collision-free maneuver. And then finally, we can script longer reconfiguration sequences. So here pivoting a chair into a table into a couch. What is this? Okay. So I just talked about this project where we embedded lots of electronics and actuators into every module in order to achieve assembly. But those of you who work with modular robotics know that ultimately we want to get to a place where we can create these high resolution structures with lots of individual modules. But as our modules get more numerous and more small, trying to embed actuation and control and electronics into every module becomes a really kind of tough challenge. And so this final project was our, in this final project, we worked to, instead of embedding electronics into every module, we came up with a way to program magnetic materials such that they could autonomously, selectively latch on particular faces without the need for any electronics or actuators. And our goal for the test is we could use materials alone to achieve self-assembly without any external control. And so as a brief introduction on magnets, one reason we wanted to use magnets was because they're all around us already. You see them in tool racks and charging connectors and cabinet doors. But if you've played around with these before, you'll know that they're kind of very unpredictable about how they're going to behave, right? So if you have 100 magnets on a table, every north pole is going to want to try to attract every south pole. I know that video is fun to watch. I should have left it playing. So magnets bond to each other unselectively, right? And so key to this work is how we program magnetic materials to assemble selectively to particular target faces. So to demonstrate that we can use our program materials alone to self-assemble, here we show how 8 cubes programmed with our magnetic codes can self-assemble in tap water under stochastic agitation from that pump on the right. And so the key behind this is that we took these little 3D printed cubes, coated them with a magnetic material, and then we program every face with a magnetic signature, where key to their selectivity is the orthogonality in the underlying signatures. In effect, what ends up happening is that if you program 2 faces to bond to each other, they'll mate, and 2 faces that are not supposed to bond to each other just bump off to each other. So the way we built these is we 3D printed these little cubes, we coated them with a self-magnetic material, and then we built this little hardware add-on with 2 magnets. One of these had its south pole facing down, one had its north pole facing down. And then we can write some G code to stamp these faces to create these different magnetic kind of codes. So every face is programmed with this signature that's kind of like a binary value bitmap, like a QR code, where every blue pixel corresponds to a north pole, every yellow pixel to a south pole. And we can cast these as a binary valued matrix populated with 1s and -1s. And so the key behind this work is kind of enforcing these selectivity requirements, which we can describe in terms of 2 rules, a local rule and a global rule. And so to explain the local rule, suppose we have two faces, A and A prime. A and A prime are complements of each other. So wherever A has a blue pixel or a north pixel, A prime will have a south pixel. We want A and A prime to bond to each other in one configuration, but not to allow them to bond in any translation or any rotation. And the global rule just says that we don't want any face within one pair to bond with any other. We don't want A or A prime to bond with B or C, etc. So I know we're coming up on time, so I'll kind of gloss a little bit quickly through how we actually generate these codes. And I'll skip ahead to the kind of key results, which I think highlights the kind of key insight here. So this slide shows the cross correlation between two of these mating pairs. So on the z-axis, we have the normalized force between two faces. And X and Y, we have the cross correlation. So you can imagine all we're doing here is we're taking two cubes, we're putting them on top of each other, we're predicting the force between them, and then we move them pixel-wise, we translate them one pixel at a time, and we plot the force. And so there's kind of the normalized forces range from maximum repulsion at 1, maximum attraction at -1. And here in the middle, between these extremes, we have magnetic agnosticism. So when these two complementary faces are directly on top of each other, place 0, 0, they're perfectly attractive. And this is by design, right? Because wherever face A has a north pole, face A prime has a south pole. That's by definition. But under translation, the net force between these two faces becomes bounded around 0. And the intuition here is that the matrices are designed such that under translation, all the attractive forces and all the repulsive forces cancel out. And I kind of, I skipped through how we generated these matrices for the sake of time, but the key here is that we generate these matrices based on Hadamard matrices, these Hadamard matrices are square matrices whose rows are mutually orthogonal. And by doing some searching over many, many matrices, we can find matrices who kind of guarantee that we have these very small cross correlations because of the orthogonality between all the columns and all the rows in the matrices that we compare.
Is it possible at all to try and encourage it to repel instead of just saying these two parts don't go together, so let's make them agnostic? Is it like mathematically feasible to say pairs that we want to connect attract and pairs that we don't want we want them to repel?
I think it must be yes. Because you can certainly you have to design two faces such that they share a lot of the same polarity. So you can imagine one face with just a ton of north, so to speak, facing poles, and another face that looks very similar. So as long as they have a kind of a high number of equivalent polarizations, then they would be naturally expected to repel. So I just kind of showed this complicated graph, but I just want to show a really simple demo of how this works. So here I have two cubes, and the faces are programmed with these selected codes. And we can actually view these codes with magnetic viewing filament. And when we superimpose these cubes, they're going to attach to each other. But when we translate them pixel-wise, they become agnostic to each other. They don't want to interact. And the same is true in rotation until we come back to our initial configuration. Okay, should I kind of start wrapping up pretty quickly? Yeah, okay. So yeah, in the last few slides here, all I really wanted to show was a couple of examples, try to give you an intuition for what the cross correlations look like, given some kind of input codes, and then show you a really quick glimpse of our UI, which basically lets us kind of manually kind of click and place north poles and south poles, and this will automatically generate G code that we can use to automatically stamp our many big surfaces with. Then finally, I was just going to wrap up, summarize what we talk about how we are envisioning doing assembly at these three levels: machine level and the part level and the material level. Yeah, I just will quickly thank all my wonderful collaborators. I'll echo, I think, a sentiment that went out by email. I say, if you're looking for PhDs or postdocs, please get in touch at any time. I would love to collaborate or work with folks. Thanks very much.
Also, could you combine the pivot with the interlocking pixels?
Yeah, so I think that would be really interesting. When we were exploring, one version of that marriage is to replace these magnetically programmed pixels with an array of electromagnets. And so you can imagine having a kind of an array of electromagnets that you polarize in different kind of configurations to get two objects to either attract or not attract. But attract each other only in one configuration, so that if they slide slightly, they'll attract each other much less. But I think certainly just kind of programming the faces of cubes and getting them to latch stably once the pivoting technique, once the pivot is completed, I think is a great thing to do as well.
How long will the 2x2x2 self-assembly take?
So that video, that took around 32 hours.
Oh my God.
Yeah. So what's interesting is that the first couple of assemblies happen within seconds. So at the beginning, there are many more pairs of cubes that can assemble. And so in just a couple of minutes, you typically see, say, 3 pairs of cubes already having been assembled. And then you have this problem known as the last, I think it's called the last part problem. So you can imagine if 7 of your cubes have assembled, say 10 hours in, it might take hours and hours for that last cube to find exactly the right spot that it needs to bond to. So of course you can do better things. Our goal was to show that it's at least possible to do without any control, but you can of course add more intelligence to your forcing to try to speed that up.
All right, let's just say no.